Okay. So Pinaki already gave introduction to most of the things I am going to talk about, and he also covered all the scales starting from micro, mesos to macro. But there is only one thing which is probably missing. That word is this nano. So I will touch that, and that will be end of all the scales. Okay, so I think these things are not needed given the morning's introduction. But anyway, let me tell you that the kind of systems I am looking at are these glassy systems which occurs in all different forms, including starting from metallic glasses which has huge practical importance, then paints, SketchUp, colloids, and avalanches or whatnot. So you just name, and most of the things are amorphous in nature. And there is this interesting thing which about this amorphous system is that their strength sometimes is much better than even crystalline materials. But the main problem is that they fail very catastrophically. So the yielding process, if we can understand, then that will actually help us to make better material in some sense. And so let me quickly tell you why we are interested to study this, because we want to also tell you why the physics in glasses are somewhat difficult and not yet been properly understood. In crystals, the plasticity is carried by these defects, and then if you look at the defects dynamics, then you more or less understand what is going on. But in glasses or amorphous solids, the whole matrix is disorder, and defining defect or some this is also now it's called soft zones or STZs, shear transformation zone, is a question which people are looking at. Pinaki already showed some of these pictures, but whether they are the one where things happens or not, that's not clear. So given a material, and even if you can find out where the soft spots are or the weak zones are where the modulus will be low, it's not guaranteed that material will actually locally fail there. So this is a big question which people are trying to understand, and but let me now move into slightly different things which are on the nanoscale. So the same physics, we are not able to yet solve the macro scale physics, but anyway let me just talk about what happens to the physics when you go to nanoscale or small length scales, where the boundary becomes very important. So why I want to study this? Because now metallic glasses at small scales are very important, and these are very fascinating objects, because when it goes from liquid to solid, there is very little change in volume. So when you prepare certain devices, the precision of or the smoothness of the surfaces are extreme. If you do it with the crystal, you don't get this kind of precise instruments. So if you can, so this is taken from this Yale group, and there are lots of other applications. So, but the main question which we should ask is that, are these material at nanoscale behave very similarly to the bulk, or there are something else which is happening? Okay, this I can easily skip. I think there are. So let me tell you who are the collaborators. So this is my student who did this work, and my friend from IIT Mumbai, Ratul Dasgupta, and Jürgen from Dusseldorf. So now come back to the physics at nanoscale. So some time ago, experimentally in the group of Franz Papen was showed that if you take amorphous solids in terms of a pillar, and then you try to compress it and see how they fail, how they break. So what he showed that if the diameter of the pillar is above certain scale, which is somewhere around 200 to around 500 nanometer or above, then you get clear shear bands. So the stress localizes, and there is a strain localization also, and then you get shear planes, and the system fails like this way. But if the diameter of the pillar becomes smaller than certain scale, which is let's say 500 nanometer, then you do not see this kind of shear band, and it breaks in a more homogeneous way. So you go from heterogeneous to an homogeneous yielding process. This is under compression. So people have also looked at similar things under extension, and you see that those cases sometimes the material can crack, sometimes you can get a nice neck. So this is kind of reminiscent of brittle to ductile transition as you decrease the size of your sample. Though the characteristics of failure changes as you go to small scale. So and then there are a lot of things which is being talked about, and they say that because of the surface the physics changes completely and you expect to get it, which is somewhat trivial. Okay, so these are more experiments, but I can skip some of this. So there was this work which appeared around 10 years ago. So they looked at metallic glass, and this glass, metallic glass, at the bulk, if you can just strain only 2%, and then it will fail very catastrophically. But if you go to order of 100 nanometer scale, then this becomes like a chewing gum. So you can actually stretch it and form a very nice neck, and it actually goes to atomically thin layer before it can detach. Okay, so then as physicist and computer simulations guy, so I looked at also some of this in very generic glasses, not metallic glass yet. So we looked at just usual binary glasses. The physics in metallic glasses are slightly different because the potentials that you have to use are somewhat more complicated than this. But I expect the physics of what we found here will be somewhat generic. So what we looked at, we take this kind of glassy systems, equilibrate and go to the low temperature regime, and you define two walls, the boundary, and then you start to pull. So this is a simple experiment we are doing here, and ask the question at what strain this material will completely fail or it will detach. So the two parts will detach from each other. So the strain I am defining is this capital gamma, which is the maximum strain the system can handle before it fails completely. Okay. So this is what we found for one such situation, given a certain strain rate, the rate at which you are start to pull, and give different temperatures. What you see that okay, so before that I have to define one more thing. So in this study, what we are changing is this height, and we are just keeping the lateral side L to be fixed for all the samples, and I am going to change H. So I define an aspect ratio which is H by L, and I am emphasizing aspect ratio because that turns out to be the one parameter, is not the length of the surface or the open surface which controls it. The aspect ratio seems to be very crucial. It is more geometric than the open surface relaxation. For large aspect ratio, which is more like a bulk, what you see that as you go towards smaller system sizes, then indeed the material starts to become more ductile, in the sense that you can actually load or strain much more before it can fail. But then it reaches a maximum value, and then it starts down. So it's not that you can go to arbitrarily small scale, but and then the system will behave as if it can support more load. It's not. So there is a critical size which seems to be very generic, and then we ask the question, what is this critical size and why the critical size appears in this situation. So what is interesting also, we found in the same case that until this critical size, all of the samples will break via neck formation. So you will have a chewing gum kind of effect, and then just after this aspect ratio, you will have precisely one cavity. Then here you will have two cavities, then here you will have three cavities, and then go on. So you can have 4 and 5. So they appear very in a nice pattern, and the cavities also are placed in a very homogeneous manner in some sense. They do not appear in arbitrary places and not kind of haphazard way. And so this was somewhat puzzling, and just to tell you that I am not claiming that this is a transition from cavity-like to necking, but if I take data from this point, then I will get necking, and if I take data here, I will get cavity. This is that precise. Okay, so this is sharp enough. And this physics continues to hold even if you do it at different temperature, different strain rate. Only the place where this cavity to necking happens, the changes. And there are certain kind of power law which appears. Let me skip all of that. The same physics holds even if you take go to 3D. Okay, so you can take a bar like geometry and pull it and ask the same question, do you see something similar? And you indeed see similar things. At large aspect ratio in the bulk limit, it starts to fail quickly, but as you go to smaller size, then the amount of strain it can support is much more. So here 1.4 means you can actually do pull the system 1.4 times its own size. And then again, so in this branch you have necking, then there is single cavity, then there are more complex things in 2D, in 3D. So this is one situation where you have a single cavity and this plane is taken exactly in the middle of the bar. But if you go to aspect ratio which is larger than this critical aspect ratio, then you see that instead of 2 cavities, you will have 4, because now there is a cylindrical symmetry. So 2 cavity is not symmetric along this plane. So you need to have at least 4, and the next one will be 5, and then that way. So so you have this situation. So so you have this cross section. Then you can have one cavity which is, because this all these boundaries are open, and the next one will be 4, which is also symmetric. Then you can have one more, and then you can repeat this pattern. And so these are all observations which looks the nice patterns appears, but the question which remains as why there is a critical aspect ratio. What is it that controls it? Then we try to look at let us say what happens to the curvature of the open surface. So let us study that. So we computed the radius of curvature by just fitting this open surface area and then fit it with an ellipse. And if you plot that curvature as a function of aspect ratio, then you see that as you make the aspect ratio larger and larger, the curvature curvature starts to saturate. The open surface cannot curve as much as it wants to, and then it stops. So this is if I bring all of this center point in one place, then this is for small aspect ratio, and then this is for large aspect ratio. For larger aspect ratio, the curvature indeed increases, but it hits the saturation, and then it no longer can exceed that. If you cannot exceed that curvature, then material has no option to create more open empty space, and that's the reason why you get a cavity. Okay. And so this is the curvature as a function of strain. Okay, done. Anyway, I'm more or less close there. And so the estimates of critical aspect ratio and from the curvature analysis seems to be very like close to each other. You can repeat the same analysis for 3D case. Because of the cylindrical symmetry, you can actually take any one cut and then study same thing, because you can have a rotational symmetry, and you get back the same physics. So it's the open surface and its curvature which controls it, which also tells you that even if you now take material which is bigger than twice in size, this physics will continue to hold. And it's not the open surface to bulk ratio is the curvature which controls this physics. So it's more geometric in nature than anything else. And so this is in this publication, in this archive post, you can have a look at it. And just to point out that the size is not what matters. So if you take a very big system size, then you get if the aspect ratio is smaller than critical aspect ratio, you get necking. Even if you take very small size but aspect ratio is large, you get cavity. So I will stop here, and thanks for your attention.
Yeah, thank you.